stealth technology, the internet, GPS in the palm of your hand, autonomous operation.
Technology is a driver of our times. Since its founding in 1958 in the midst of the Cold War, DARPA, the Defense Advanced Research Projects Agency, has been a driver of technology. Welcome to Voices from DARPA, a window onto DARPA's core of program managers. Their job? To redefine what is possible. My name is Ivan Amato, and I'm your DARPA host. And today I am pleased to have with me in the studio Mr. Paul Thomas, known since his day one as Rusty, because he arrived in the world with red hair. Since September 2017, Rusty has been a program manager in the agency's Tactical Technology Office, which has a penchant for pursuing audacious vehicular technologies for the air, space, and oceanic domains. Already, Rusty has made it his mission at DARPA to do what he can to develop new concepts that will deliver more resilience, global reach, and networked connectivity by way of new space systems. Rusty joins DARPA from DAQRI, D-A-Q-R-I, an augmented reality services company, even though it does sound like a cocktail, where he served as the executive vice president for global operations. He also held positions in a slew of commercial space companies, among them SpaceX and Orbital Sciences. He has been in on the design and management of an amazing portfolio of space-related programs, including the SpaceX Dragon spacecraft, the DARPA Micro Satellite Technology Experiment, or MITEX, the Iridium Low Earth Orbit Satellite Constellation, and the U.S. Air Force Geosynchronous Space Situational Awareness Program. His initial training for all of this came in the form of a Master of Science degree in Aerospace Engineering from the University of Texas, Austin, and a Bachelor of Science degree in Aeronautical and Astronautical Engineering from Purdue University. After I say, wow, let me say to you, Paul Rusty Thomas, welcome to the Voices from DARPA studio.
Thanks, Ivan. It's great to be here today. Thanks for having me.
Before we get started on your life adventure on the forefront of space technology, I want to let listeners in on something that will not come through in your voice or words. At 6 feet 8 inches tall, you are among the tallest people at DARPA, though remarkably not even the tallest. It does make me wonder, though, how you managed to fit into those thin shells when you were on the Purdue crew team, and if your fuel costs when you fly your own Piper Dakota plane are higher than they would be if a 5 foot 8 inch guy like me were the pilot.
Well, yeah. So it does cause me a lot of pain on airplanes these days. That is true. But I'll tell you, being tall was great. I grew up in Indiana, and I learned to play basketball, and for some reason I was kind of good at it because of that. So being 6'8" is a good thing overall, and I'll take it.
All right. Well, one of the things I always want to hear from program managers who are with me in the studio is where they got their start and where their interests came from in science, engineering, and technology. So I want to put that question to you.
Okay, yeah, great. Well, I'm an aerospace engineer, as you said, and like a lot of aerospace engineers growing up in the 70s and early 80s, really saw what NASA was doing. My grade school had special readers where you could go in and see the history of what NASA had done even back in the 60s, and I remember poring over those in great detail when I was a kid. The real kick for me became a career day that my school was having in 8th grade where they actually pulled my father in, and I realized that my dad, a mechanical engineer, and my grandfather, his father, a civil engineer, had been doing some pretty interesting things their entire career, and they were staying on the cutting edge of what was going on. My dad worked for General Electric in the plastics industry when that was getting big in the 60s and 70s, and my grandfather worked for Northwest and put in all the airfields when they were doing the Orient Pacific routes through the 40s and 50s. He also helped design the LaGuardia and other airports. So had 2 generations of engineering behind me, and at that career day, I actually had my dad was one of the people presenting, and he walked through the different types of engineering, and at the bottom of the list was aerospace. I did not know that was an option, and all of a sudden it clicked for me that aerospace engineering is something I could do, and I could focus on it and continue on and do what I saw my dad doing in terms of really innovative things and new concepts that could be set forward. So with that, I was in state for Indiana, and Purdue is a great school, so I jumped at the opportunity, got accepted there. So while at Purdue, we had quite a few amazing professors. One of them, Professor Andrasani, would give us talks about how you could do no better in your career as an engineer especially, if you stay on the cutting edge and advance technology, advance what humanity can do, In the back of my head, those words have rung with me for the last 25 years. If I kept moving to where is the most advanced technology and how can I help the most?
Well, those sound like two great lines of influence. I mean, a dad and a teacher like that. And wow, have you run with it? So one of the things I would like you to do here is to take our listeners on a kind of whirlwind tour. So you can't really dwell too much on any one thing you've done. I mean, your CV is just one of the most amazing documents I've ever read.
Thank you.
But if you can take us for a whirlwind tour on your experience in the commercial space sector.
Commercial space, absolutely. So I did an internship at a small engineering services company, and I got to work on NASA with the space shuttle back in the late 80s. But what really got me going on the commercial side was right after grad school, I got the opportunity to go to Motorola, who were firing up the Iridium low Earth orbit constellation, proliferated low Earth orbit satellites that were cross-linked and providing global connectivity to the entire planet.
And this was a large constellation.
Very large.
How many?
66 satellites plus spares. So the goal was to build one satellite per week and launch the entire constellation of 70 or 80 satellites, including the spares, in 1 year. Never been done before. And to do that, we were going to use a large number of launch vehicles. And Motorola had never designed a spacecraft before. So they put all that together, and back in the 90s when this was happening, the Motorola had a really good plan. They pulled in a lot of experts. They pulled in subcontractors like Lockheed and Raytheon, who were experts in this area. They put together the team, and we ended up building at a rate of one spacecraft every 4.3 days. We launched from 3 continents in just over in 8 days, 14 satellites, and we launched all the satellites in about 18 months.
And actually, before you move on to some more of your commercial space experience, I remember just talking with you at another time when I think it was on this project, the Iridium project, which took you around the world to some of the other space cultures out there, like in China and in Russia. So I'm just wondering if you can compare and contrast a little bit of the kind of space cultures that that you have experienced, being part of ours here and then witnessing those elsewhere.
Absolutely. Well, the first thing I noticed is when you get to any other country, any other location that's doing rocketry or spacecraft design, you really run across a type of engineer that you can relate to really well. The people that do that are very similar no matter what culture they come from. I was very amazed how quickly you can make friends with the Russians or the Chinese, anybody who were actually launching, because we were launching on the Proton rocket 7 at a time with the Iridium, and we were launching 2 at a time on the Chinese rockets, 5 at a time on Delta IIs which was our main launcher out of Vandenberg. I would rotate between the launch bases in California, Baikonur, Kazakhstan, where the Proton rocket was launched. Also would go to Moscow for the integration meetings, over to Beijing for the Chinese integration meetings, and Taiwan for the launch bases there. It was a very interesting program, and really I found that the Russians and the Chinese, well, the Russians invented rocketry as we know it just at the same time we did. China was coming up the curve. They were getting faster at an incredible rate. They were getting better at an incredible rate, and I found that both Russia and China, their cultures were less analytic than American aerospace cultures. They were very much driven by build test cycles. And I found that really in the commercial space here in the U.S., we're served pretty well when we do those type of things. When you move out of the analytics, don't spend a year or two trying to figure out exactly how to optimize a problem, but build something that may be a suboptimal, test it, and then use that result to go to the next phase and turn the cycle.
And when you say analytics, I think of modeling and using models and data to try to optimize.
So one thing one area we're really, really good at in the U.S. is very good computers and the very good computer algorithms that let us analytically predict what a rocket will do under a structural load or under guidance navigation control algorithms, which is great, but it doesn't really tell you everything that could possibly happen during a flight, whereas a flight actually does tell you that.
Before we move off of this little block where you're describing, this international framework for getting so many satellites up in such a short amount of time, share with our listeners a kind of funny experience that you had with the Russian team when they were trying to figure out what they should actually call you.
That's a great story. Thank you. So when I started working at Motorola, we would have every other month we'd have a technical interchange meeting with either the Russian launch team or the Chinese launch team. So you'd have one each month. When the Russians would come to town, or when we would go to Moscow, we would have the stereotypical long tables with all the Russians on one side and all of us on the other side and the translators. when they asked and we introduced everybody, they got to me and I said my name was Rusty Thomas. They stopped the meeting real briefly and they started talking to the translators, and they came back and said, "Is that your real name?" And I said, "Well, Paul's my real name. I was born Paul Thomas, named after my grandfathers, but since the second or third day I've been around, Rusty's been a nickname." And they went back and talked about it, and they said, "Okay, we get it. Pavel, that's a good name. We're going to call you Paul." And I said, "Well, that's fine. Some people do call me Paul, but most people here at Motorola know me as Rusty." And they ended up coming back and saying, "Well, we're going to call you Paul, and the reason is we've discussed it, and we don't have the nickname Rusty here in Russia, and we just don't feel comfortable calling anybody Corrosion." So so they decided not to call me Corrosion, and I was Paul from there. And I've been Paul on and off since that time.
Okay, because of that, it was a smooth working team. That's
yes,
fantastic.
It was.
So now I want to take you back to that whirlwind tour of your experience in commercial space that I wanted you to do, but I took you on a diversion. So let's get back to that. You talked a little
Absolutely.
bit about the Motorola experience. Now move from there.
Motorola was great. Then I moved up to Seattle, following where is the most advanced technology happening. Seattle in the late 90s was a really happening place for a lot of reasons. They had also a new company that was founded called Teledesic, had some money coming in from Bill Gates and Craig McCaw, titans in the communication and computer industries. And they wanted to build a global low Earth orbit satellite constellation to do broadband communication called Teledesic. We got pretty far into that design, but the technology at the time wasn't quite there. Miniaturization, as we know it today, really wasn't there. And the dot-com crash of 2000, 2001 made it really hard for us to get financing. So we ended up not going forward with that program, even though we had gotten FCC license for a lot of spectrum, and it had a really good chance to be a major success. And it was, at its base, a very compelling architecture. I moved from there and did engineering services in San Diego. Had a really good time in some of the early days of UAVs, Predator and Global Hawk. I got to be a consultant down there for the early UAV designs, and then moved to orbital sciences, where I got into the government side a little bit. And then after keeping the commercial side going, after the orbital sciences curve, I went to SpaceX. That was in 2011, and worked as the senior director for Dragon production, building the capsules that go to the space station. So I spent 5 years there, and had just an amazing run putting all those capsules up. Also got to work on the landing legs and play a good part in the historic landing of those first stages.
Right, and just weeks really before this discussion we're having now, a Dragon capsule did arrive at the International Space Station for a resupply mission. So when you see that, I mean, how do you feel knowing that you had been part of that? Intense
pride, absolutely. That was a turning point in how we do space missions, how NASA contracts for things, how NASA moves forward the technology, gets to the cutting edge, develops it, and then can move that technology to companies like the SpaceXs of the world, who could then use that to build a commercial case, and then allowing NASA to move on to the next place. When I was at SpaceX, we went from doing one rocket a year, one Dragon every year or two, to 4, 5, 6 Dragons per year, and now SpaceX is ramping up to 20, 30 plus launches in a given year. It's really been an incredible time to see that approach to how you do commercial space turn on and become a reality, and then become a success, and then become really a major success where it's at right now.
Okay, so you've sort of told the story already here of you kind of growing up professionally along with the commercial space sector, which is just kind of an amazing thing to think about. But you then made a decision to say yes when the offer came through to become a program manager here. I'd like to hear the sequence of events that led you in this stage of your career from the commercial activities you've been in and now here as a first-year PM.
Absolutely.
Program manager.
By chance, I happened to, in the early 2000s, be talking to some friends at Orbital Sciences, and they said there was a very interesting program that was firing up called MITEX. I didn't know much about it. It was a DARPA program It was classified what the experiments were, but we were allowed to know that it existed. At the time, it was just a DARPA experimental program to do a demo of this technology, and Orbital was looking for people who had my type of background, a little bit of commercial, but also had the right ticket so they could do the work. And they brought me out for a 3-month stint, and I was just going to help do some analysis for that spacecraft. I did some analysis, and after 3 months, it looked like DARPA was going to continue the program. Orbital wanted to keep expanding, so they asked me if I would stay on as the manager for the design of that. So I got to run the design of the MyTech spacecraft, and so I stayed in Orbital for not 3 months. I ended up staying for about 8 years. And during that time frame, we worked through the MyTech spacecraft. I got to do the design and build. We actually took it through integration, launched it, and I went out to Schriever Air Force Base as a vehicle engineer and got to be on console and fly it for about a year and a half. So it was a really good experience. It wasn't commercial, but it was government taking commercial approaches. Orbital is a commercial company, and this was an experimental process that wasn't a strict requirements-driven program. It was there to prove some key technology that we could use in space. It was successful, and I was very proud of the results there. That kind of got me into what DARPA can do. DARPA can step into an area where there might not be a set need or a set of requirements or a set funding line, and say, this is technology that would really help the warfighter, help the country in significant ways, and say we're gonna do a demo. We're gonna prove that this is possible. The proof is here if we can actually spend 2 or 3 years and some money to actually get a demonstration of it running. That opened my eyes to what you can really do outside of the commercial world, but still using commercial approaches as much as possible. So followed on from there and became a deputy PM on the GSAT program you mentioned earlier, Geostationary Space Situational Awareness Program. It's Air Force program of record now that is doing very well. It's up in the GEO, and it's acknowledged, but it has very, very good capability and is getting a lot of good feedback from the people who use it. So the GSAT program, very successful. And after it got to the critical design review, I happened to have the opportunity to go to SpaceX. They were just firing up, so I already talked about that. It was a wonderful 5 years. At the end of that, I was at DACRI doing the operations job of setting up augmented reality global operations manufacturing for what's going to become a revolution. I'm positive augmented reality is going to be a very, very big thing.
And just a 2-sentence description for listeners who might not know what you mean by augmented reality.
Augmented reality is the ability to put on glasses that will augment the information that you're seeing, real information, with computer-generated 3D graphics that actually will float in space. You can put text, you can put graphics, you can put anything you want, and it's going to be contextualized around the actual objects in space. So it's not virtual reality where it locks you out and you don't see anything. In augmented reality, you actually have still see the people in the room, you still see all the objects, but it's adding information.
And I have seen, I think, a multisyllabic phrase for this. Software-defined holographic light control. Is that related to what you're talking about?
It is in the most advanced versions of augmented reality, and DACRI had some of the most advanced holographic light control technology out there.
Okay, so now
they really did.
My suspicion is confirmed that you actually are going to develop the Star Trek Enterprise at some point in your career.
The holodeck is out there. It actually is, yeah, absolutely.
So getting back to how you actually got to DARPA.
The final turn to get me back as a program manager came when the concept of the Blackjack Constellation, which I did not come up with, it was already been formulated by experts here at DARPA.
And we'll talk a little bit more about that right after this.
Great. So DARPA contacted me and said, we're going to go forward with a proliferated low Earth orbit architecture to start to change how we do space missions. Right now we do space missions with very exquisite, very capable satellites that actually cost a lot of money, so therefore we can't build very many of them. And the low Earth orbit proliferated approach that Iridium did back with the communications in the 90s and Teledesic was trying to do, and other companies have taken it forward, is a different approach to put smaller, lower cost and in some ways expendable, but not expendable, just lower reliability. But the key element is small and lower cost satellites that are in very low Earth orbits, so that you can cover the entire Earth with coverage. And like we said earlier, it was 60 or 70 satellites will usually do it to give yourself constant coverage over the Earth. And DARPA let me know that they were going to move forward with an experiment to try to move into augmenting what these exquisite satellites can do with a LEO, a low Earth orbit, proliferated constellation. When that opportunity came in, I came in, gave a talk, and it was a match made in heaven.
Because it's not like there's 10,000 people in the world that have your background. It seems tailor-made for this kind of idea.
I really do think, in terms of a match, in terms of what DARPA wants to do with and what these type of constellations can do in the future, and my background, it's a really good match. I'm very excited to be in this position. His timing's perfect.
Let's talk about Blackjack in a little bit more detail. Tell me a little bit about kind of the elements of that, and even before we start that, can you tell listeners and me where the name comes from?
Sure. The concept of Blackjack is that instead of having sensors in space that might come out of one or two or three points of the sky, you could potentially put smaller sensors in many locations, give the destroyers or the surface action group commanders of the world, or the Army commanders or Air Force, anybody, the ability to look over the horizon with a small number of discrete sensors that actually dot the sky in some ways. Well, if you go to a casino and you look up, you see on the ceiling, you see all the little domes. Those little domes are all tiny little sensors, and they're making sure that nothing bad's going on, right? So the concept of Blackjack is to follow that distributed sensor approach that you see in a casino, where you don't have one or two large systems making sure that everything's working okay, and making sure that there's no cheating going on in the casino.
Okay, and just for the record for our listeners, we do need to point out that DARPA does not get all of its ideas from Las Vegas.
We don't get all, but probably more than we should, maybe. Yes, absolutely. So the name came from somebody playing blackjack would have this distributed sensor set around them. So it's kind of a tongue-in-cheek name, but it's a good name, and it gets the idea across when we give our talks and what we're doing. So Blackjack is just, as I said, a low Earth orbit constellation of sensors that we're going to leverage. And a key element of this is leveraging the commercial space. As I talked my career in the past, is you can do things very quickly, you can do things very efficiently with a commercial approach. Now, that's not to say that the government approach, how we've procured things in the past, is always bad. But in some cases, you don't get the optimal solution, and you could do things on a lower cost and at a faster schedule if you tackle it in a different way. So what the idea of Blackjack is, that try a different approach here. Use low Earth orbit, use proliferated commercial satellites, especially the buses, where we will marry military payloads to those commercial buses, and then start flying a large number of them, so you can give that proliferated global constant custody constellation. And I say constant custody, that means if a commander wants to look at a given spot on the Earth, he can point the sensor to that spot immediately, because there's going to be a satellite overhead at any given time.
Okay, and you've used a word in a way I hadn't heard before, proliferated. I just want to make sure I understand what that means in this framework.
Proliferated means multiple points in the space and spread out over the surface of the Earth, except up in space, of course. So any person on the ground is going to be able to look up and see a Blackjack satellite if the full constellation is developed in the sky at any given time. And then the reciprocal approach works, that if the Blackjack satellite is always going to be able to see any point of the Earth at any given time.
Right. So it's interesting. So there's some aspects sort of a GPS-like system, and that you've got many satellites working in a kind of coordinated fashion, delivering amazing kinds of data that would not be possible otherwise. Here we're actually talking about a lot more than the several dozen, right, of GPS. Talk just a little bit more about the various kinds of challenges that are part of this project. One of them certainly is producing, almost mass producing very rapidly, a lot of satellites. And so you talked about your experience there. But there's also going to be coordination. There's going to be command and control. What are some of these other elements that you can talk to us about?
Absolutely. So first of all, yes, your analogy to GPS is 100%. That is a proliferated constellation, but it's at a medium or medium-high altitude. With Blackjack, we're going to go very low, 500 kilometers to 1,200 kilometers. So a range that's just above the Earth's atmosphere for these satellites. And the trick is going to be building, since you're low enough, you're going to need more satellites than what a GPS satellite what a GPS constellation would need. So to do that, you're going to need mass production, and to do get the cost right, you're going to need to build them on very short time scales with a minimal amount of assembly, integration, and test. And to do that, we're going to bring in as much commercial approach as we can. We've had an industry day, a very positive response from over 130 companies signed up for the industry day, and we had over 275 folks who wanted to come in and listen to us. So we believe that approach, going with discrete, low-cost nodes in space, that are almost expendable, not expendable, but almost, is going to be achievable, and we're going to use that commercial and commoditized approach to the buses and bring that to impedance match to the military payloads that will go on those buses also. The other key element of this, and you alluded to that a second ago, is that if we're going to launch hundreds or more, thousands of these satellites, we don't want to require teams of multiple people per satellite monitoring them. Right now, the exquisite satellites have excellent teams of people on the ground who are making sure everything that satellite does is monitored. They're going to analytically predict beforehand what the response of any new script that they're going to send up is going to happen. It's an excellent approach, but we really want to get autonomy into the Blackjack architecture. And when I say autonomy, I mean, how does the mission control work? How does the resource planning work? How does the payload, in terms of what it's seeing, work in terms of, can you move, instead of raw data down to the people on the ground, can you vectorize that information and contextualize it to what's important?
Okay, and one of the other interesting things about the Blackjack program to me is because you're not putting, multi-billion-dollar jewels up there, large, just tremendously expensive assets that need to stay up there for years and years. Here you can do what I guess much more frequent technology refresh. I presume some of that can be done through software now and again, just the way we're always upgrading our various applications on our computers. But this also does give you some opportunity to, without breaking the bank, putting up actually new generations of these small satellites and still having them work within the Blackjack constellation. Yeah.
And there's two areas there that are very important, and we're gonna chase both of those on Blackjack. First is, if your individual nodes are in low Earth orbit, your launch cost is lower than going into higher orbits. Your weight is less, and the cost of the individual satellite is less. So we're aiming for an on-orbit cost of $6 million per node, per Blackjack node. That includes the launch cost, which means that if you have a problem with one of those satellites, you can launch another one and replace it for not a huge amount of money. And then the second piece is the ability to do on-orbit, over-the-air updates of the software. We're going to put large processors. I call it the pit boss, once again going with the Blackjack approach, right? The pit boss is the brains on each one of the Blackjack nodes. It's going to have teraflop class processor on it or more, and it's going to allow us to put a lot of algorithms on space, and not only put a lot of algorithms in space to do the work up there with those edge computers, but it's also we're going to launch more processor capability than we need for the first generation, because we expect to get better and better with our algorithms, and algorithms typically need more and more processor. So if you can, we talked about, I worked at SpaceX. My boss there also founded another company called Tesla, and one of the really cool models of Tesla is you have a car and you might come out in the morning and it's done an over-the-air update, and you have a better car the next day than you did the prior day because they've updated all the software. So I'm going to follow that type of approach, putting a lot of extra capacity for the processor so that as the algorithms get better, you get a better spacecraft essentially for free, although, of course, you have to pay for the algorithm update. But in terms of launching new satellites, you don't need to.
Mm-hmm. And I imagine you also have to think about end of service when you're talking about so many discrete parts that are in low Earth orbit. It sounds like to me that these are going to deorbit in some way or another. Have you given that thought? Absolutely, we've given that thought. And that goes back all the way to the Motorola Iridium constellation. Every Iridium satellite has the ability to deorbit itself at the end of its life. It has a small amount of fuel reserves left, that those fuel reserves aren't used for anything else other than the deorbit, and it has enough redundancy in the electronics on board so that if it starts to have problems with its primary mission, it can
still fire the thrusters and bring itself down. So that approach has been proven successful with Iridium and the commercial constellations. We're going to follow same approach with Blackjack, and I believe there are numerous FCC filings for mega constellations of communication satellites going to be out there that'll launch even more satellites than Blackjack. They're going to be good stewards, I believe, of low Earth orbit also, and put in the ability so that as a satellite ends its operational life or gets replaced with a better tech refresh satellite, it will immediately turn on the thrusters and deorbit and burn up, usually over the South Pacific or somewhere relatively benign. These small satellites don't make it back down. They burn up in the high atmosphere during reentry, make a wonderful shooting star if you happen to know where it is.
And there may be many of them in this case. So as you think about, this is amazing to think about just all the pieces and again, how audacious of a program it is. Are there one or two things about it that stand out in your mind as maybe particularly a reach, even for a kind of DARPA program, technologically speaking?
Absolutely. So the biggest reach, I believe, is the amount of autonomy we'd like to put on these spacecraft. I've given a metric that if we lose the ground control, let's say we have a comms problem or there's some type of interference and the satellites aren't talking to the ground, I want them to be able to operate at least for 24 hours as a constellation, talking to each other through their systems and managing their resources, managing the mission, and still providing whatever end effect or set of information the warfighter, the people downrange need without that ground infrastructure. So that's going to be an interesting one. And I say the metric is 1 day, but really my stretch goal is to get to 30 days of continuous operations without talking to the constellation while it still performs its primary mission to whoever needs to have that information that it's generating. So putting that into place is a significant leap forward from the current operations where you have an operations control center on the ground, making sure the satellite health and safety and the mission is being managed properly, to one where you don't even have a human in the loop. You move to you go from a man in the loop to man on the loop, where the people doing the management are there to make sure and watch and adjust priorities as necessary, of course, but they're not there to make second by second or minute by minute decisions on how the spacecraft operate and what they do.
Right.
That's a really hard problem.
So a fair amount of autonomy, but always with human beings there as shepherds and in the loop in some way on the loop.
Absolutely. Yes.
So you're a first-year program manager. Typically, program managers are here for just several years, 3 to 5. I have had some people here in the studio who have done several tours of duty as well, so people like it enough that they come here, they do 1 tour of duty, they go away, they come back. I'm just wondering if, as a first-time program manager with a program of this complexity and size, whether you think this one program is going to be enough for you to satisfy your technology interests, and just because it's going to be so hard to do, or are you already imagining taking on additional programs?
I'm actually already imagining taking on additional programs. That goes back to my theme of how do you get to the most cutting-edge element of whatever you're doing in your career. Blackjack is going to be a major program. I believe it's going to be a huge success, and it's going to really lead a pivot to low Earth orbit. But once you start working in the low Earth orbit regime, and once the DoD and DARPA starts working and putting these systems into place, I can envision many other programs that will leverage this type of architecture and the success that will come out of Blackjack. Once we build this global mesh network, this internet and space, the space ARPANET, how can you use it to actually benefit the people on the ground? And I think there's a lot of program areas.
And I just want to point out to listeners that even though Rusty is talking about a program like that, it does not mean that it is automatically going to become one. He's going to have to really jump through a lot of hoops and convince a lot of people that that's something worth doing. So this really is essentially a glimmer in the eye that may or may not come to become a program. So that's one. I mean, it sounded like you might even have more ideas.
Yep, I got a few. I've been spun up with a world of augmented reality on what you can do with light control. Holographic light control is an area of high interest to me. I believe that we are approaching that point where the holodecks of the world, not where you can touch things that are appearing, but the ability for systems to transmit holographic light, phase control the light, and project it in a way that you are immersed in a reality that isn't real, but it seems real because your eye is getting fed the same information it would be if the object was actually there. I believe that type of light control is just around the corner, and there's a good chance it's going to revolutionize how we do to interaction with computers and interaction with even people in the same way that the transistor revolutionized how we do computers. And I think that's coming the next 5 to 10 years, and I really hope to get DARPA moving in that direction.
As you were listing the potential applications of that, training just popped into my eye. I mean,
training is a huge one.
Yes,
in fact, not just training, but if you're if a military person is deployed and you can have a holographic surgery show how to fix somebody, and you're deployed or in a very remote area, you can actually train somebody in real time to how to do something because they can see it in 3D right in front of them as it's happening while they're doing a medical procedure. Training for welders or training for other industrial applications becomes much more advanced, much more fast. If they've already done the studies showing you can train somebody anywhere from 2 to 10 times faster with augmented reality tools and these holographic light approaches, because your brain is programmed to absorb information from 3D context much faster than you are with someone talking to you or reading it in a book. So when you see it, you absorb it faster. So I think training is going to be an area that's going to be revolutionized by
right.
this
And another thing just came to mind is ergonomic sort of discovery. So you might have a space and you want to figure out the best way to arrange things in that space. With this kind of technology, you'd be able to test out 1,000 different ways very efficiently and cheaply.
That's right. One of my early career moves was that internship where I got to work on NASA projects, and we were developing 3D CAD at the time when 2D CAD was the standard.
Computer-aided design.
Computer-aided design. And that three-dimensional CAD allowed you to mock up engineering parts and then do fit checks, virtual fit checks, making sure the parts wouldn't interfere with each other. And that was a huge boon forward. It really changed how engineering design was, mechanical design. I believe the same thing will happen when we start doing this with interactive, collaborative tools that allow everybody to walk in and see what's happening in 3D space without even needing the computer screen necessarily in front of them.
And then there's one other kind of technology project that you worked on, which also just represents to me just how many thousands and thousands of technology and engineering issues there are when you're really thinking big. So you also were in on the design of the crane operation for mating satellites, going into kind of vehicle dispenser components. Right?
Yeah,
So
absolutely.
it's just one of the many things.
So this was an interesting invention. We worked as 2 or 3 of us at Motorola. The problem we had was that Motorola was pitching the ship and shoot approach to spacecraft, which you finish it on the production line, it went into a shipping container, it sat on the dock until whether the Russian Proton or the Long March, Chinese Long March, or the McDonnell Douglas Delta II folks needed another set of satellites, and those launch campaigns would go, and the Russians would need 7. And if that was the case, we would call FedEx, and FedEx would show up at the Sky Harbor Airport, and we would load 2 or 3 satellites at a time. They would fly them to Russia. We'd load them up, and then we'd get them out to the launch base, and we want to put them on the rocket within a day or 2. And that's obviously not how INT is done right now in the satellites. We were looking for very fast cycle times, very quick process flow. And to do that, we needed to mate 7 of these satellites that were very close to each other accurately and quickly. So we put together a crane, I think we call it the swing and twist Eliminator, which mounted to the floor of the Russian integration hall in Baikonur. And every satellite would be brought in a vertical state, attached to this, and then the Russian crane normally would swing these around a little bit as they moved in because you didn't have any other neighbors, you didn't have any other satellites right next to you. But on these dispensers, there were 7 like wedges. They were all very close to each other. So you had to control the twist and the swing. We got to the point we could mate 3 of the satellites per day and have all the entire dispenser of 7 satellites ready to go after 3 or 4 days of processing, and then they would be fueled and be ready to launch.
Okay, so on top of everything else, you're a crane guy. So, you're working on things that many of us would consider to be kind of science fiction, technology fiction, though you're going to make these things real. Are there non-space technologies that you just go nuts about?
Non-space, well, I'm going to stay in the aerospace without the space. So let's go to aero. And I do believe that transport of human beings on this planet is going to get to the point where we're going to be able to move at hypersonic scale in the not too distant future. It's not an area of research for myself, but I'm exceptionally interested, I guess curious, on how we're going to get some of the new technology that seems to be coming online worldwide to the commercial space, and how we might start moving people from let's say New York to Sydney in hours instead of the 12 or 14 plus hours it takes right now. I think the very high-speed transport, which I guess it doesn't hit your mark because you will probably have to go into space a little bit during part of that flight, but I still see some very high-speed flight, supersonic, high supersonic speed flight as being an area of interest, of significant potential in the next 10 to 15 years. And I think there's going to be some teams that will start cracking that open a little bit.
And so sort of ironically, thinking big in this way to make the world a little smaller, in the sense that you can get from any point A to any point B in a much shorter time than
That's right. I mean, Blackjack will give you the mesh network and communicate it at broadband, and if you can actually move the people, that's going to be the next step up.
So, Rusty, you are a technology developer. You've been doing that your whole life, but you also have taken time to get into more of the mindset and the setting of the warfighter, the warfighters who you're now trying to serve by bringing more capability. Can you just share a little bit with listeners about your experience in that context?
Absolutely. So I've been a reservist for United States Navy since 2004, and as an intelligence officer, I was lucky enough to be selected to go to Naval Special Warfare Intel School, and actually went out during the surge to CENTCOM areas, desert areas, with SEAL teams to help do targeting and high value targeting. We did a pretty good job. We got to move through those areas and picked up quite a few of the Al Qaeda mid-level operatives and put them away. So I'm still active. I drill down in Little Creek on every month. A very, very important part of my life. Although it's as a reservist, it's a secondary element.
But I also imagine that boots on the ground experience now as a program manager completes a kind of loop for you that not all program managers can have.
I think it does help. The area that I think it helps the most in is when you are downrange with special forces, special operators, the amount of bandwidth, the amount of sensing you can get, just the amount of communication you can do is very limited. You're typically moving data through a soda straw, and what I'm trying to do with a program manager here is to give those type of deployed sailors, soldiers, Marines, whatever they are, the ability to move data at much higher bandwidth and to get data from sensors that are over the horizon, not necessarily organic to their own unit, immediately, within seconds, back to where they're at without having to go through a ground infrastructure. So seeing how it's operated when I've been downrange is really helped shape how I'm setting up the technology for the future of what DARPA can help here in terms of next generation.
Well, so Rusty, you've taken me and listeners on an amazing tour of someone who has been in the absolute thickest part of these last couple of decades of just the evolving space technology. So I want to thank you for doing that. It's really been a pleasure.
Oh, thank you. It's been I've had a great career. I'm happy to be at DARPA and looking forward to what the next doors get to break down and where we're going to be on the cutting edge next year.
And thanks, listeners, for sharing this time with us. I hope you join us again for the next Voices from DARPA. For more information about Paul Rusty Thomas, the programs he and his colleagues in the Tactical Technology Office runs, and the other breakthrough technologies DARPA is working on, visit darpa.mil. And for links that enable you to download the podcast, go to the Voices from DARPA page on DARPA's website.